Okay. Okay, hello everyone. Good afternoon. Today very hot. If you're using the air conditioner, means that it will be very pleasant sleep. Okay. Anyway, what I would like to start with today is a little bit continue from what we have yesterday. I think a few more exercise and a few more examples. Uh, if we see this, the last one that we did, the integration, and I think using the series approach to transform particular functions into a series is one way to approximate how the series will or how the integrations will be at the end of the day. Okay. So, for example, if we want to take these integrations, okay, we can take with the series, and if you want to maybe, let's say, take from certain points, we can try a few terms. For example, if we are able to take the, let's say, take from 0 to 1. Okay, let's say from 0 to 1. Now, what we did is we're going to remove this constant, right? And then take this. And let me erase this part. Okay. And write another few terms just to make it a little bit longer. So this will be 7, okay, 7, 3, and then maybe 9. And then minus dots. And then we plug in 0 and 1. And of course, if we see the pattern, we can ignore the 0, right? We can just focus 1. And to approximate the 0 and 1, what you need to focus is look at the denominator here. We can see that this is 3, this is 5, 2 is 10, right? It's 7, 3, 2, 6, 7 is 42, and it will increase. And at some point, if you want to maybe make some limitations, that the decimals that we want, maybe 5 decimals or maybe 6 decimals, we can stop until that terms, and then we can just compute all the terms. Okay? Maybe just taking calculators and compute all the terms. Like for example, if we want to make, let me take this a little bit to the right and maybe resize a little bit to make space. So we can take this and we can say that if we plug in 1 for x, we can compute these terms, and we can say that this is approximately, we want to stop until this terms. Okay, so we are going to stop until this the fifth term. We are going to stop until this fifth term, and we say that this equal 1 minus 1 over 3 plus 1 over 10 minus 1 over 42 plus 1 over 216, and you can compute, and if I just write the final result, this is going to be 7475. Okay. Because if we want to look on the terms that is maybe after this fifth term, so the sixth term, so when n equals 6, it's become x 11 divided by 11 and then 5th factorial, right? And if we see this is at x equal 1, this is 1320, which is less than 0.001. Okay. So if we want to make sure that maybe if we want to make sure the error, if error, then this is our result. Okay. So how many terms we need is depends on how many error we want, how many decimals we want in the calculation. Because the terms after this part will be meaningless, right? The decimals is not our requirement. That's one thing. Okay. So today and Wednesday, I will try my best for at least a half part of the course. We're going to take some time to review and practice. I prepare some exercise after this few page, and I think I'll also put the exercise later on the Moodle, so you can check later on. Okay. Okay, just a little bit review. Okay, I think yesterday I got a question from one student. So if you want to build up Maclaurin series, for example, for this ln 1 plus x, as usual, we take several terms, take derivative, second derivative, third derivative, or if you want to make it 4, 5, it's okay. And then substitute the x with 0, check the value, and then we can write the formulation for the Maclaurin. So formulation is this, okay, for Maclaurin. We change all the derivatives with the value, and then I think this is the one that we got, okay. And remember that I think at the third derivatives we need to get these two, okay. How we can get these two is from this two, this down here, right? The derivative. And if we want to look more derivatives to come, we can see that this will be 3, right? In the fourth, and then in the fifth, we'll see 2, 3, 4, right? And we can say that it's a factorial. Okay. So we can say that these terms here will be a factorial, right? This will be a factorial that will cancel out our factorial that is in the denominator. So we can say that this is going to be 2, 3, 4, 5, and so on. Okay, that's how we get. Okay. Now, if you want to try, you can try the tangent inverse. Okay, I will not doing that in class. So I hope you can try by yourself for tangent inverse. So try build Maclaurin series for function the tangent inverse x. Okay. And I do hope you can review all the basic Maclaurin, and you can try to build up by yourself from the scratch, okay? So that in a sense you will know how the process going on. Because if you can build up by yourself, then it's safe to say that for the Maclaurin, for the basic part, you are well, you can hold on yourself based on what the process will be. So try your best to build up the Maclaurin series from the scratch. Try the other function as well that is on the basic Maclaurin, such as the sine. I think we've done sine in class. Cosine if you want, try to build cosine. Try to build the tangent inverse. Okay. And since we are able to exchange the function and the series, so in a more like calculus notations, for example, the integrations, or if we have like a limit and we need to, maybe we can solve it also exchanging the functions with certain series. I think that can be done. That can be done as well. Okay, I will make a new page for just a few notes that we can have some examples. Okay. Okay, for limit, okay, let's say we have limit, just like your old calculus 1 exercise. And I think it's up to you. Okay, if you're given a limit, if you want to work out the limit as usual, you are maybe using L'Hopital rule. If you see if it is the indeterminate forms, you can go for L'Hopital rules. Or before we are trying to solve this, try to check the value itself. Okay? Make sure that we are in indeterminate form before taking L'Hopital, right? Now, aside from taking L'Hopital directly, we can try to exchange this into series. We know the e to the x, the series, right? So for example, we know that the e to the x is, we can write as a series and we can write a few terms just for reference here. Okay, now we can take this e to the x and then exchange to the function that is inside within the functions. Okay? And I think it depends on the limit. Sometimes it is very useful. Sometimes maybe just taking like the regular limit, like usual, maybe that will be faster. Sometimes it will be very fast. Okay? And I think this case, not really. I think 50-50, you can still take the older way to solve the limit or taking the series inside the limit. Unless the question specified that you need to do this exchanging series, then you need to do this series. Okay. If not, then you can do it with any method. Okay, so write down the write down the terms. 1 plus x. Let me just write 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 minus 1 minus x and over x squared. Okay, now we can see the 1 will cancel out with another 1. X also cancel out, so we are left with this x squared and so on and so forth. And then we can divide with the x squared. Now divide with x squared, meaning the x component on the numerator, the power will be reduced by 2, right? So this will be 1, this will be x, and the other terms will be x squared, x cubed, and so on, right? So we can have the limit at the end of the day. This will be half in the front, and you will see that this will comes out nicely. And we don't really care much about this part here because we can just exchange with 0, right? So the answer will be half. And sometimes, if you are able to do it in your head, like perhaps if it's like as simple as this one, then you can try take out directly 1 and x, and then you can write the other part of the terms defined by x squared, and then you can simplify this. And I think it's also quite useful in some way, especially if the limit has a complicated structure and it has the basis series for the Maclaurin, like the basis function. Like for example, the e to the x, or maybe sine, cosine, that you can exchange those functions with specific series and specific terms. Yeah. I think you can do L'Hopital rule, right? So yeah, you have options. Or if the questions may be asking directly to use series, then this is the way. Yeah. So you can treat the series, okay, as substituting the functions, and then you can write a few terms and then do some algebra. Okay, and then I think next example will show you more possibility for the case of the algebra. Okay, another example is if we want to combine some Maclaurin series. Okay, for example, if we have e to the x sine x. Okay. We want to know like the first few terms, okay? Maybe 4 or 5 terms, what's or maybe 3 terms that usually a typical questions that will be asked. Write 3 non-zero first term from these functions. Now to look at this e to the x and sine x, we can first write down that e to the x or maybe let me write until 3. And then we have sine x. Sine x is start with x, right? And then the second part is 0, and then we have the third part. So we can say it's negative here. It's 3 factorial, right? Okay, and then we are going to multiply all this. Okay, so we are able to write down this multiplication of e to the x and sine x. So basically we are going to multiply all this with this, right? And multiply the other part. Okay. So this will be x plus x squared, right? X plus x squared plus x cubed over 2. I'm still on the red line. X cubed over 2 plus x with power of 4 over 6, right? Okay, that's the red line. And this is supposed to have dot like that, okay? Because it's actually having more terms. But let me just go through the light blue. So the light blue, we are going to have negative x cubed over 6, and then negative x with power of 4 also over 6, and then I will just write this 2 first, and then minus with a few terms, because the question is asking only the 3 first terms, right? So I don't need more terms. Okay, I just stop here. Okay, I wouldn't want to complicate myself. So we'll just stop here and then adding all the terms now. So ex sine x is, so x plus x squared, and then the x cubed, half minus 1 over 6. There will be 3 over 6. 3 over 6 minus 1 over 6 is 2 over 6, so it's 1 over 3. So plus 1 over 3 x cubed. And if you want the fourth, we can also take down, but I think it's become 0, right? Okay, so I will just stop until here, and this will be plus dot dot dot. Maybe they will be another terms. But this is the first three terms, 3 non-zero first term, that is going to be for the function e to the x sine x. So it depends on the question how many terms that we need to write down, because we don't really need much terms here, because we need only 3 first terms. I can stop this tree. It's still okay. Eventually, it will be 1, 2, 3, at least that is the terms, and we need to just plus the other one. Okay, so that's one way to see the multiplication. We can also use division. Okay. For example, the tangent x. I think I will just write on this page. Let me resize a little bit. And then make it to the this one. Okay, now we can also write, for example, a tangent x. Okay. And then we can see the tangent x as a division sine x over cosine x, right? And then these two trigonometric functions, we know the first few terms. Okay, so if the question is asked the same thing, write down the non-zero three non-zero first term, which means that we are going to take this and then write the terms for sine x and cosine x. So x minus and then plus, and the cosine is from 1, and then the even number and alternating. Okay, to deal with this, we are going to just to use the long division. This is x minus x cubed over 6 plus x5 over 5 factorial is 5, 4, 23, 120, right? Okay. 1 minus x squared over 2 plus x4, 24. And what we need is just a few terms, like for example, these three terms, okay, just for our computations. Okay, we can start with x, right? We can start with x to cancel the first x. Okay. So this will be x minus x cubed over 2 plus x5 over 24, and then minus x will be cancelled. Now negative x cubed over 6 now become plus x cubed over 2. So it's x cubed over 2 minus x cubed over 6, which is x cubed over 3, right? And 24, if we multiply with 5, it's become 120, right? So 5 over 24, over 120, it will be minus, let me write here, just to make sure. So it will be 4, right? Negative 4, 120. Or negative x5 over 30, right? And we have another terms, right? Okay, and we need to cancel out this x cubed over 3. So we need to plus x cubed over 3 to make the cancellations. Okay, and then minus x5 over 6. Okay. And this will be cancelled. And this will be 5 over 30 minus 1 over 30 is 4 over 30. So 2 over 15, right? 2 over 15 x5. And to cancel out this one, we need to add plus 2 over 15 x x5, right? To cancel out this, and that's it. This is the 3 terms. Okay, so at the end, the tangent x can be represented by these few terms: x plus x cubed over 3 plus 2 over 15 x5. Maybe I will erase this one here. This is maybe confusing. This is my calculation. Okay, we're going to see some practices, some exercise. I will show you some exercise problem from the textbook. Okay, let's see the example. Okay. So how to deal with this question is basically we are going to exchange the basic Maclaurin series. Okay? Exchange x with the with something that is inside this function now. For example, the first one, or maybe not the first one, maybe the, but let's say the number 44. Let's say look at number 44. So we know that ln 1 plus x from our table or from our Maclaurin series is the sum we can move one by one. So let's say we are going to exchange x with x cubed. Okay, so this will be x 3n, right, over n, and then multiply with the x squared. So right here, so x squared ln 1 plus x cubed is x squared, I think, let me, so sum and then we can just simplify the terms inside the sum and then moving out the x squared inside. X 3n plus 2 over n. I think that's the one that we are looking for. You may try the other function as well. I will focus on the next type of questions. You can try the other one. Maybe try the sine pi x over 4. So the idea is to exchange the x with the value that is inside these functions. Okay. Oh, this is number 44. Number 44. Maybe later I will put all the questions for the Taylor Maclaurin in the Moodle. You can try the other question as well. Okay. Let me go through the other type of questions here. This is using some computations. Okay. So both question is asking computation for the error need to be on the 5 decimal places. Okay, so it need to be correct within the 5 decimal places. Let's say we are going to try number 56. Okay, so use the Maclaurin series for e to the x to calculate 1 over with the base square of 10 of e, or we can write this is actually e negative 1 over 10, right? Now we know that the e to the x, and this is supposed to be, you need to have a familiarity with this e to the x, okay? So 1 plus x squared over 2 factorial plus x cubed 3 factorial plus dot dot dot. Okay. So this e negative 1 over 10 means that we are going to exchange all the x with the 1 over 10. So 1, and then exchange x with negative 1 over 10 plus, this will be 1 over 10 squared. The negative will be positive, right? And then over 2, and then plus, or say negative because it's cube. And then how many terms we need to add, okay? We need to check, okay? We need to check. Either you check 4th, 5th, or 6th term. Okay? In this case, the most significant will be the 5th. Okay? So when you check, check 5th, which means that this will be 1 over 10 with power of 5 over 5 factorial. This will equal to, if you check the calculator with calculators, to 8.3. Okay. Yeah, because of the negative 1 over 10. Okay. Yeah. So this value is not affecting the 5th decimals. So I think we can stop until 4. Okay. So plus until 4. Okay, and then you can check your calculators to get the answer. And also, as you may see as well, this is also alternating series. I think it's still okay if you want to look at as an alternating series. Okay, we are going to have a break and continue the exercise for the next break. Okay, okay, let's continue for a little bit. I think for the integrations like this, the key points the same as before. We take the inside function first. And see the basis for these two. This is the sine, okay, and then the arctangent. So exchange the inside x, okay, with x squared, multiply with x squared, you get the sum, right? You get the sum of the series, and then you integrate the sum, and that will be your answer. And this is also the same. Then inverse, you get the sum, exchange the x with x squared, and take integration. Take the integration of the sum. Okay, another questions, a typical questions that I think important is finding the sum, like this whole question here. So let us start from this number, or maybe let's start from the quite easy number 83. Okay. Let's look at this. So we know that if we have the sum, so the process is we're going to find what kind of function that is represented within the series. Okay. So this is negative 1 to the power of n factorial. Okay. If you remember, this will be the e, right? The e to the x. In e to the x is this x, right? So which means that this is going to be, we change the x with negative 1. So e with power negative 1, or 1 over e. Right? Okay. So we take that. So since the e to the x is right, so this will be e with power of negative 1, or 1 over e. And then let's look on 84. Okay. 84, you have a factorials here. So you need to get a glimpse what kind of functions that in their respective series, it has this factorial. They can be sine or cosine, right? So it has 2n, so probably cosine. But now we have the 6 and pi with power of 2n. It's both value. It means that maybe we need to combine this together to get a more simplified form. So perhaps this is going to be sum so let me write the pi over 6 on this top, and then 2n factorial here. And this is the cosine, right? The cosine x, if you remember. This is sum. So this will be cosine pi over 6, which is half square root of 3. You can try 85, 86 if you want. Okay. And similarly, if you look at 87, it has 2n plus 1 factorial, so probably sine. But we need to make sure we look up this 2n plus 1 here, it has the same power. So maybe pi over 4, 2n plus 1, 2n plus 1 factorial, so sine is sine of pi over 4. So that's the process. Now there's three questions here from 88 to 90. What we need to do is we need to find a pattern, and then somehow we are going to write down the sum from this pattern. Let's maybe start from 90, or maybe 89. Or let's start 90. Let's start 90. For 90, we see that we have 1, 3, 5, 7. It's an odd number, right? Odd number. So we have 2n plus 1. And then we have 2 cubed, 2 to the power of 5, 2 to the power of 7. So it's basis 2 with power of the odd number, right? With the odd number. So 2 with 2n plus 1. Okay? So it's 1. And then it's sum. Oh, and then it's alternating, so we need to have alternates here. So -1. So it's supposed to be, if the first one is positive, so positive, so if n equal 1, it's supposed to be, n equals 0. So n equals 0, it's 1, it's 2, okay. I think just n should be okay. When n equal 1 is negative, it's 3, okay, it's correct. Okay, now we have 2n plus 1 in the bottom. So it's not a factorial, so not sine and not cosine, right? And it's an odd, it's a tangent inverse, if you remember correctly to the basis. Then we could write down, then maybe we need to rewrite this in a more clear way. Now I'll move other than 2n plus 1. So I will write half with 2n plus 1 on the top, and on the bottom we have 2n plus 1. Remember that, and right on the left, that the tangent x or tangent inverse x is sum So this will be tangent inverse of half. Okay, you can check 88, 89. Okay, and let's try number 92. So it has the functions x over 1 plus x squared, and we need to determine the derivative of f 101 times at x equals 0. So first, we need to go back to the coefficient that we need to write on the Maclaurin, right? So we have the fn 0 over n factorials, right? The coefficient. So that's the coefficient for the Maclaurin. But before going to the coefficient, maybe we could take this functions and write down its series. So we have x, 1 plus x squared. I think we can remember the 1 over 1 minus x, the geometric series. Okay, if you remember the geometric series. So 1 over 1 minus x, you have minus x, it's changed to this negative x squared, right? And then multiply with x. Maybe let me give you a couple of minutes to think and try. the f 101. Remember the coefficient in the Maclaurin. Okay, so the functions we can rewrite as, so the terms can be done by taking this into 1 minus x squared, okay? And we can rewrite this in terms of the sum. This is negative x squared and then n. And then this will be x and then x to n, and I will move x inside. To n plus 1, right? Okay, now because we need to find the f 101, which means the derivative at what 101 times, right? We need to derive 101 times. Then this part here, we need to find that when x is 101, right? X with power of 101. Remember that our coefficient for the Maclaurin is f n 0 over n factorial, right? Now, we get x with power of 101. So let me write, we got this at n equal 50, right? At n equal 50 is 101, right? And when n equal 50, this is even number, this is positive, right? And we get negative 1, 50, x 101 is x 101, right? Okay. So the coefficient, because it's even number, it's just positive 1, right? Coefficient is 1, okay? So it means that this is the Cn, okay, this is the Cn. Okay. So this, okay, divided by 101 factorial is equal to 1, right? So the f 101 0 is 101 factorial. Okay. And some questions might ask you this type of questions. It means that you need to connect the relations between the the F coefficient, or you can write the whole Maclaurin series with this coefficient as its main point. It should be coefficient, right, multiplied with the active power of n, right? That's the Maclaurin series. Okay. Any questions on this? We get from the Maclaurin. We get from this. This is Maclaurin, right? Okay. This is Maclaurin. So first is we want to make sure that the n is 101 because we need to make this 101. And from these functions we get this relation. So we get the relation for n first. We get n. To get it 101, we need to get 50. And then check 50 for the whole series here. We get negative 1 power of 50 x 101. So this will be the coefficient, right? Coefficient is 1, which means that this is the whole thing is 1. Then this is supposed to be 1, and this is the one that we asked. So we one, yeah, one. The question is directly asked this one over here. Okay. Okay. Actually, I would like to go for the next chapter, but I think I will just take some time for you for reviewing all this. I want to mention. I think on our last online test, I need to emphasize this series. Okay, you have the questions that is asked the 1, 3. If I'm not mistaken, this is the question. This is 2n minus 1, right? And then I think this is 2, 5, 8, 11. This is 3n minus 1, right? Yeah. So you have the series. This means it is going to multiply 2, 5, 8, 11, and another term here, and multiply until 3n minus 1. This also multiply until 2n minus 1. Okay? So, if the question is asking you to is converge or diverge, I think many of you write the result as diverge. Do you think it's diverge? Okay, let's take a while here. Take the ratio test. Okay. Now look on the terms here. So 1, 3, 5, 7, and then until 2n minus 1. Okay. So this will be plus 2, right? Plus 2, plus 2, right? So if you take n plus 1, it need to be plus 2, right? So 2n minus, so plus 2 plus 1, right? Okay. And then 2, 5, 8, 11. This is 3, 3, 3, right? And then you have the 3n minus 1. So the next term is plus 3. Okay? So 3n plus 2. So that is an plus 1. So this will be. But I think the problem is to understand what this actually means. Some of you think that this is the whole series, and you just calculate this. And of course, if you check the divergence test, it's 2 over 3. Oh, it's diverged. Okay, but this is actually, we need to multiply all until the 2n minus 1. So an plus 1 is 1, 3, 5, until 2n minus 1, 2n plus 1. This is n plus 1. Also same thing here, 3n minus 1, and then n plus 1 is this. Yeah, need to include. It's multiply. And then multiply 2, 5, 8. But the interesting in these calculations, all the terms that is multiplying is cancelled. Okay? At the end, it's cancelled.
But if you don't take them into account in the ratio, then it's wrong.
Yes. Okay. So of course, this is going to cancel. So by the ratio test, it's 2 over 3, which is less than 1, converge. Okay.
You specify next time
Yeah, because I think
I thought the right
I
part
think
is a
the
description
conclusion,
of
right?
yeah.
But in short, tips, if you check some exercise that I've given, every time you see factorials, every time you see these multiplications, da 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 da, you should use ratio test. Done. Okay. No need to use other tests. But that conclusion came from the most frequently exercised. Okay. That is on the textbook. Yeah, I think I will stop until here. Okay, I will give you more maybe exercise to prepare your midterm. We still have Wednesday class. Actually, I prepared to have another practice, but I want to move on to next chapter. So maybe half part only for the Wednesday, and the other part will be focused on the next chapter. The next chapter is not going to be from the early part of the chapter, the factors. I will start from the middle. So hopefully you already get familiar with the factors before, right? So I will just start from the middle. Okay. Yes?
Multiple choice and midterm.
No choice?
Last year.
Yeah, but you need to write down explanations. I'm thinking. Okay, I'm thinking.
Maybe somebody.
Okay, I think we can have a feedback